and welcome to our last lesson. We're combining 4.8 and 4.10. 4.9 is a learning check, so we use class time for that. In 4.8, a couple definitions. The interpretation of the y-intercept, it's the value of y when x equals 0. And in context, it would be something like the starting time is 0. And then the predicted y context is the y-intercept, so that's the height or location, whatever it is, when x is 0. In interpreting the slope, with each additional x context, the predicted y context will either increase or decrease by the slope. And usually we have what's called a unit rate. We'll do something like $15 per hour or 60 miles per hour, something like that. And we'll do a couple problems with that interpretation, as well as for 410 using the least squares regression line or line of fit. So if we look at this data, ages of American women at first marriage, the age is depending on the year, and as we've gone through time, it appears that the age has increased. So we have a positive correlation. The scatter plot shows the median ages of American women at their first marriage. The line of best fit has an equation given here where in the initial year, 1960, we would expect a woman to be married at age, the average woman, at age 19.845, so almost 20 years old. And every year since 1960, we would say that there's a increase by 0.126 years. So 0.126 years added for every year since 1960, where X represents the number of years since 1960. Use your equation to predict the median age of American women at their first marriage in the year 2025. And what we want to notice here too is we're using the years since 1960, so we wouldn't plug in the number x equals 225. We would plug in the years since 1960, so that's 40 up to 2000, and then another 25, so it's 65 years. So you can see we've plugged in 65. There have been 65 increases of 0.126 roughly, and then plus the 19.845 for a total of 28. We would assume, or predict, I should say, extrapolate out to 2025 that a woman age 28 is the average age for getting their first marriage. Use your equation to predict the year when the median age was 25. So here we're going to look for 25 and see what the corresponding year would be. And if you look, it should be right around 2000, but we're going to use the equation. It says use your equations. You have to show work, otherwise you won't get credit on the test. And we set y equal to 25 and solve for x. That means we undo a plus 19.845 with a subtract. That gets us down to 5.155 equals 0.126x. And then to get rid of the times 0.126, we divide by 0.126, so 5.155 divided by 0.126 is 40.9, and 40.9 years since 1960. So we've solved for x, that's a year since 1960. To get the year, we would add this to it. So it's almost 2001, really. It's 9/10 of a year into 2000. Which prediction, age 25 or year 2025, are you more confident and why? And the important thing here is we're pretty confident with this data, but we have a hard time using this to extend out into the future or even back to the previous years. So age 25, it's near the other ages, whereas 2025 is quite far away. This age is maybe a good prediction, but it's outside of the data set from 1960 to 2015, something like that. So we would feel pretty confident about any predictions within this range. And the word we use is extrapolation, which is a prediction far away from the observed data. Our data was observed before this 2010, 2015. So we're going out quite a ways. and we would have a little less confidence with that than any of the numbers within this year, which was, in this case, 2000. So I'm going to do two problems. They're related with 4.8 and 4.10. Scatter plot shows the average starting salary associated with the number of years in college. Line of best fit has the equation y hat equals 2.9x plus 21.9. We want to rewrite the equation in context. Basically, we're just going to look at the units and say that the starting salary hat is related to the years in college by this. Starting salary hat equals 2.9, that's the slope, times x, which was years in college, plus the y-intercept. That's how you do an equation in context. For each additional year, what is the meaning of the slope? What it means is for every year of additional college education, your salary is predicted to increase by $2,900. What's the meaning of the y-intercept? That's going to be this number here. It's when we've got 0 years of college. So when you don't go to college, your predicted starting salary is $21,900. Use the linear equation to calculate the predicted salary for 5 years of college. So somewhere out here, we assume, but we're going to use the equations. We're going to plug in 5 for x. Do the math, 2.9 times 5 plus the 21.9 is 36,400. Use the linear equation to calculate the predicted number of years in college for a starting salary of 60. So now we're looking for the outcome of 60 somewhere out here, it looks like. How many years of college would be required? Are you confident in your prediction? As we said, that's going to be outside of our where our data was taken. Doesn't mean it's necessarily not going to work, but we'd have less confidence. So we set y equal to 60,000. We're just going to solve for 60 and have our answer in it's in thousands. So 60, we're going to subtract the 21.9, get the 38.1, and then divide by 2.9. We'd say 13.14 years, so over 13 years of college, which doesn't seem like you'd go to college that long. So no, we're not real confident. It's too far from the observed data. And then you can see we fixed the 60 here. It's in thousands, so we wanted to keep that without the 60,000 there. Okay, here's another example, very similar. If you could go through this, see if it makes sense, and then you'll see the answers here. You can see how your thinking is working here. Consider the scatter plot below made by Tricia, who keeps track of the number of gallons she puts in her car and the number of miles she drove since the last time she filled the tank. So this will get her economy of using gas, miles per gallon. The line of best fit has this equation. We missed the x in our initial when we wrote this. So looking at y hat equals 28.8x plus 18.1. We want to rewrite the equation in context. So what is the meaning of the y and what's the meaning of the x? This is the estimated miles, or the miles hat, equals 28.8 gallons plus 18.1. What's the meaning of the slope? That's your miles per gallon. So for each gallon of gas, your car is predicted to go 28.8 miles. Why doesn't the y-intercept make sense? So if we think about what a y-intercept is, it's the value of y when x is 0. So if you have 0 gallons, you're still getting 18.1 miles. And you really can't go 18 miles or any on 0 gallons of gas, unless you're going down a hill, I guess. Use the linear equation to calculate the predicted distance traveled. So we're just plugging into this equation, or this equation, where we have 12 for x. X is the horizontal axis here, it's the gallons. So if you plugged in 12 here, multiplied and then added, you get 363.7 miles. Use the linear equation to calculate the predicted gallons of gas needed to go 400. So looks like for 12 gallons we'd get 363. So for 400 miles we would need more than 12. But let's see how you solve this. 400 equals our right side of the equation, we're going to subtract the 18.1, and then we're going to divide by 28.8, and we get x equals 13.26 gallons. 400 is pretty much in our realm here. It looks like it's a little bit outside. You'd say it's okay outside the data, but not by much. So yes, and this seems reasonable to need 13.26 gallons. And that should be enough information for you to get cruising on the homework. And if you have questions, we'll see you in class.